Hello, everyone, and welcome. This is a video on coupling and cohesion while we're building our better software. So what we're going to be talking about right now is going to be specifically why software modules should be like good coworkers, focused and independent. So we're going to talk a little bit about these two different concepts and how they contribute to our code. Okay. So let's just start off with this idea of why should we even care about these things and doing better in our code. So the key points here are really that clean design helps reduce bugs and increase the flexibility in our code. This idea of coupling and cohesion are two key factors in modular design. So as the course progresses, we will discuss other factors in modular design, but these are definitely two that we want to pay special attention to. Especially if we ever find ourselves doing any kind of work that may be may require some cross-platform functionality, so different front ends. So perhaps running an Android application versus an Apple application, right? An iOS application. It may just be as simple as that, but there are also scenarios that matter for different browsers potentially as well. So we use this idea of coupling and cohesion to help decide how we're going to split our code up, how we are going to get into these different modules. So just some quick definitions here about the difference between coupling and cohesion. So first, let's talk about cohesion. We're basically talking about how closely related a task is within a single module. So if we have multiple tasks, how connected are they within a single module? And I'm using the term module pretty loosely here because it could mean within a specific class, but it can also mean potentially within a specific method or a package. It really just kind of depends at what level of abstraction we're looking at our code from. Basically, cohesion is how well a team works on a goal. How well does the whole team, the whole module, the whole class, whatever it might be, work toward a single goal. Now, coupling is how dependent each module is on one another. So again, this can be method related, class related, package related. It really depends. And in a more, I guess, metaphorical sense, it's how often these teams need to interrupt each other to get a job done, right? How much communication is actually happening between teams? How interwoven are they? Kind of brings us back to this picture of interwoven lines versus our sort of cleaner organizational system. Okay, so let's start by talking about coupling. This is just sort of an overview of a few different types of coupling, but there are others depending on who you ask. I'm just kind of giving us a little bit of a spectrum to be looking at here. So first we have this low-level idea of content coupling. Content coupling means direct instantiation, pardon me, and we're going to look at an example of that in just a minute. We next have on our spectrum of types of coupling, common coupling. This would be when we are sharing global variables. So when two different methods or classes or packages or whatever it might be sharing common code. We see this in our own code when we do our application package. So a lot of us, if not already, but will soon, have a package that all of the other packages are sharing. We can even see this in our objects, right? Our object package, pardon me, our domain objects, they are being shared by all of the layers. And that's okay. I'm not saying it's necessarily a bad thing. The way that we're using it makes sense. We keep the logic out of there to keep that coupling as low as possible, given that we are using shared code in multiple places. Next is this idea of an external coupling. External coupling depends on external formats. So basically us relying on, CSV formatting. So saying, a method is expecting a certain format of file. It has to be formatted a certain way for our code to be able to handle it. We're definitely coupled tightly with that format. So that would be external coupling. Next, we have this idea of stamp coupling, which I'm sure a lot of us are going to do inadvertently. This is when we pass a whole object into a method, but we're really only using a very small part of that object. This basically exposes parts of an object to a method that maybe it doesn't need to expose. And so this is this idea of stamp coupling. And then lastly is sort of the loosest form of coupling, which is this data coupling or parameterization, where we only pass things into a method that the method actually needs and uses. We keep our data as separate as possible and only pass around the information that actually is required to be passed around. Within each of those within each of those functions. Okay, let's just look at what really bad coupling might look like, this idea of content coupling, because I think it's where a lot of us end up with a lot of our code ends up starting, basically. So here we can see code that is really poorly coupled. And by poorly coupled, I mean tightly. It has very tight coupling between methods and classes. So here we have a class engine. It has a public variable, fuel level equals 100. We know that our instance variables should be private. So immediately we can see that everybody has access to this variable, and that's no good. Next, we can see that the class car is going to be right here, directly instantiating this engine class. So both we have the new keyword directly instantiated inside this class, and we can see that our engine class type is not abstract, right? This is an instantiable class. It's not an interface. It's not an abstract class. So both of those are forms of bad coupling because now we cannot easily change the type of engine, right? New engine means if there's different engine types, we'd have to come in here and change the code to have a different engine type. It also means that we're directly tied on this side to only one engine type. So this is creating some technical debt of if we ever want to have different engine types, we'd have to come into the car class and make changes in here, which we shouldn't have to do. And we'll talk more about that next topic in the solid principles. We can also see right here that in this method void drive, we can directly manipulate that fuel level. So here when we drive, we drop our fuel level by 10. Of course, this seems totally fine because when you drive, your fuel level goes down. However, this allows us to bypass any potential validation that the engine class may want to have. And it allows us to make careless mistakes that the engine class may be purposefully trying to avoid, right? Like dropping below 0. There's no way to stop the car class from sort of doing whatever it wants. So we really want to try to hide that data away. We want to encapsulate our data better. We can avoid a lot of these tightly coupled decisions with things like encapsulation and dependency injection, as we will see when we talk about solid principles. All right, the other term that I mentioned was cohesion, and we have a similar sort of scale for the types of cohesion. So first off, we have this idea of coincidental cohesion, where we end up just sort of grouping random tasks together. This often comes in the form of some kind of utility class. Very frequently, we see this in smaller projects or early on in projects when we feel like we don't have enough difference in functionality to create multiple utility classes. So instead, we kind of just make one that holds all the miscellaneous utility that we need. It happens all the time. Next, we have this idea of logical cohesion, where we start grouping tasks. We start grouping functionality by the type of task. So perhaps you have like a validate function or a validate class, right? So all the different types of validation are in the same class and they're all related by that same idea of validation. Next is temporal tasks, and temporal is tasks that are done at the same time. We won't necessarily see a ton of that within our code, but we might a little bit where you find yourself doing a bunch of validation and you just throw it all in one method because we're just going to do all of it at the same time and then it's done. So they all end up in the same method. It may not happen at a class level, but it definitely happens at a method level. Following that on our scale here, we see procedural, communicational, and sequential cohesion. Now, this is often what we do in our early years, and some of you may also be doing, and it may also form from some forms of logical cohesion. Now, I say this because often when we write our code, when you're doing a first or a second year assignment, as you're working through your code and you realize, oh, I need to make another method, you just make that method directly below your current working method. So you just kind of pull that functionality out, which is a good first step in your decoupling and in your, uh, you know, intent for strong cohesiveness. But we basically just end up with methods that are all, once again, coincidentally located temporally close to each other. They're just one after another because we are in this place of just putting all of our code as we're writing it in the same place. And then at the very end of the spectrum, where we have really strong cohesion, we have high cohesion, is functional cohesion. And this is where everything works toward one goal. So as opposed to being related by a task, oh, everybody validates, so they're all in one class together. We're actually working toward the goal um, of finishing some kind of responsibility. Now, this definitely is a tricky sort of line to walk here, and we'll talk more about that in just a minute. I want to just show sort of this idea of poor cohesion. So poor cohesion means low cohesion, right? We want to have high cohesion. So low cohesion here, we can see a utility class where we have a bunch of like random methods um, that are kind of all together here that just don't really make a lot of sense to all be in one method. They're all kind of miscellaneous utility activities. So let's just bring all of these together. We can see here, I've kind of put together a chart of the different things that might happen. So first we have this idea of high coupling and high cohesion. And this is going to be a team of experts all sharing one inbox and one phone line. It's probably pretty productive, but everybody's always stepping on each other's toes, right? Nobody has defined responsibilities because it's all in one place. Um, Next, we have this idea here of low coupling, and high cohesion, a team of experts with clear responsibilities who communicate via email. So this is kind of our ideal situation right here. This is uh, a team of individuals who know exactly what their job is and know how to communicate with each other when they need help from a teammate. Over here in this quadrant, we have low cohesion with high coupling. This one here is everybody doing everyone else's job while constantly calling each other for help, right? This is basically just chaos. This is complete chaos all the time. Our code isn't focused. Our individuals aren't focused. Everyone's doing things that maybe aren't even related to their job. This is real bad, which makes sense given that it's in the exact opposite quadrant of the ideal situation, which is right here. And then over here, we have low coupling and low cohesion. This right here is the idea of basically a bunch of interns in the office, right? No one knows exactly what they're doing, but at least they don't interfere with each other. Everybody's doing their own thing in their own corner, but we're not really all working toward a goal of any kind. It's kind of um, everybody in their own world. Okay, so let's just take a look at some code here. Here we can see we have some code for an app. The app gets started off in main, right up here, and the app begins to run. Okay, when run gets called, we can see that we simulate some user input, we simulate some logic of like greeting the user, we make our pretend database over here and we fill our pretend database, and then our UI can go ahead and output the greeting, right? We can see how this might be something we would have written hopefully in our first year and maybe started to move away by the end of it, or definitely by our second year. So how exactly can we turn this into better code? We come over here and we can see the after, and the after is over 2 slides. So just hold on here. We can see we have, and this isn't perfect either, when we reach solid principles and the topic of solid principles next topic, we'll see this in greater, we can further decouple our code and follow better design principles. But certainly this is better than before, where each of our different tasks are individually set. Our main is still kind of like our manager. It gets everything up and running, but each task has its own responsibility. We can get the information we need from the UI right here in string user input. We can get the generate greeting information right here from the logic. So we call our logic layer. We generate our greeting based on the very specific input it needs access to, and it will return it back. We can then store this user input in our database. The order of these doesn't really matter, it would seem, and that's okay. But we can see that the data store calls it itself. And then we can see that the UI will show the greeting. Again, we don't actually want to have main in charge of all this information. This is a very, very high level explanation. Because of course, in our projects, our UI is going to talk to logic and logic is going to talk to database. So you'd never have a UI and a database call happening in the same method or even in the, like in main like this ever, really. So here we can see the UI class has been created. We can see how we're simulating getting our users input. We can see that we have some method here, this show output method, also related to UI, not necessarily related to getting input, right? One is getting input, one's showing output, and this is coming from that greeting. So pardon me, these aren't exactly temporally located to each other. If we go back to the previous slide and think about that, but we can see that they're both UI related, and that's really what we're aiming for in this type of a program. Here we can see all we have in our logic thus far is generating our greeting. Perhaps some logic should be in here, some other logic like validating that the name actually is a name. It's not an empty string. Stuff like that could be included in this, but a reminder, this is just a very small example. And then we have our data store, which actually creates the database over here, our fakey database with space for 10 strings. And when we save it, we increase the database size. We can see right here that if there's not enough space, nothing happens. Perhaps this should be throwing an exception or something like that. But again, think small example here. So some of our common trade-offs that we really need to think about include the fact that sometimes increasing cohesion can temporarily increase coupling, right? We might introduce a helper class. And this is how we end up with those like utility classes that do everything. It is a balance, and we really want to be careful not to go extreme on either side. So a good rule of thumb is to minimize coupling without sacrificing our functional cohesion. And it is possible to over refactor our code. We don't need a million methods just because we really want to get everything as tightly as high cohesive and low coupling as possible. These sort of design principles are about the conversation, the planning, and making the best choices that we can at the time, right? So if we think back to that unavoidable tech debt quadrant, it's this idea that we can't necessarily avoid refactoring and we can't avoid technical debt, but we can have really good conversations with our team that hopefully lead to really good discussions and reasoning behind our code at the time. If I were to come into your code base and ask any of you, why did you make this choice or why are these methods all in this one class, you should be able to tell me why. You should be able to tell me the discussion you had and the reason behind it. And there's no right or wrong answer necessarily. It is about that discussion. It is about being able to say, well, these are the things we expect to happen in the next 6 weeks, and so we wanted to prepare for them. Or these are the things we don't ever intend to add into our code, or not for many, many years. So we didn't see any reason to do X, Y, and Z. Things like that. It really is about that discussion. So let's very quickly play a game here of high or low coupling. I would recommend basically pausing when I say pause so that you can try it and then you'll get the answer from me. So here is a Final Fantasy team of 3 players. Each has a specific role or a set of skills. We pretend that a healer can only heal, a melee DPS can only attack or hold weapons, and a tank can only defend or hold shields. So do we think that this has high or low coupling? Now is when you should pause and think about it. Okay, so this would be an instance of low coupling. This is low coupling because each individual character on our team, each player has a very defined role. They're not stepping on each other's toes at all. Nobody can heal but a healer, and nobody can defend except for the tank. Let's look at this exact same team, but with this idea of cohesion. Do we think that this has high cohesion or low cohesion? Now is a good time to pause and consider it yourself. This would be a team with high cohesion. This is because each team member has a very clearly defined role and they can follow through with their own role and responsibility. And as a team, they are working together toward a goal, right? To win whatever it is they're trying to win. I don't know. I'm not a big Final Fantasy player, if I'm being honest. But they are working together as a team. If you remove one of these pieces, we no longer have a fully functioning team. We can't necessarily achieve our goal without all the different members of our team working together. So we have high cohesion but low coupling in this Final Fantasy team. Let's play again. Pardon me. Here is a Lego Millennium Falcon build. And the question is this high or low coupling? Now is a good time to consider this for yourself and pause. This will be a situation where we have high coupling. We cannot get to the engine room without taking apart the rest of the build, right? If we put a person who's some, little Lego minifig right in the middle, how are we going to get them in and out? How can they do their job? How can this thing fly without all the pieces tightly attached together? They must be attached together for this to work. I'm not saying that's necessarily a bad thing either, because in this instance of a Lego build, it makes perfect sense that the pieces are tightly coupled together. They must be clicked into each other for it to work. It makes sense in this scenario, but it absolutely is an instance of high coupling. Let's finish this off with these Pokemon. Here is a Pokemon team, and let's discuss whether or not we believe that this synergistic, balanced Pokemon team has high or low cohesion. This team of Pokemon has solid coverage of offensive and defensive maneuvers. And what this means specifically is that more than one Pokemon can cover a range of abilities and skills. It's possible that there are duplicate abilities and duplicate skills given this specific team. Is this high or low cohesion? Now is a good time to pause. This is a team of low cohesion. Again, not necessarily a bad thing, but it is the reality. It means that it's possible that we have duplicates and that we're maybe not, we could step, like each Pokemon could step on each other's toes, right? If one Pokemon came in and tried to put their enemy to sleep, but another Pokemon had already done that, then it's a useless move, right? We have this redundancy that maybe is unintentional. It also might mean that our team worked really well together. If one team member, faints, the other five team members can still pick up the slack. The team doesn't completely fall apart the way that it would in our Final Fantasy scenario, right? If in our Final Fantasy scenario, our healer fainted, we'd be effed, right? We wouldn't have a healer anymore. Or if our melee DPS character fainted, we can't attack anymore. Like that's a huge problem for our Final Fantasy team, one that we don't see happen over here in our low cohesive Pokemon team. Again, perhaps it makes sense in this example, uh, but it may or may not make sense in your code. We can, using these examples, hopefully start to see why it's not necessarily um, so extreme that we're always aiming for perfection in terms of coupling or cohesion. Part of it is just being able to make the case of why we made that choice. So having those discussions is what's really, truly important in this topic. Let's just finish off with a general summary. In general, we do want to minimize coupling. It keeps our modules independent. It means we can easily swap out an Android UI for an iOS UI. We do want to aim for that in our code. Same with cohesion. We want to maximize cohesion. We want to keep our modules focused on a specific goal to the best of our ability, while of course also minimizing redundancy. Often this leads to groups who make 30 classes, each with one method in it. And of course, that comes back to what I said about over refactoring. It really, truly is about striking a balance, having those group discussions, and being able to defend our reasoning as to why we made the choices we did. It really all boils down to good design, focused modules that don't really need to gossip with each other. Now, next class, when we discuss the solid principles, we'll be able to dig a little bit deeper into how we have these discussions and how we identify scenarios that may require some refactoring around coupling and cohesion. For now, I will just say thank you so much for your attention, and I look forward to seeing your low-coupled, highly cohesive code in your next iteration. Thanks all, and have a great rest of your day.